Happy New Year. Good. Today I want to first review everything that we did already in terms of GLM analysis of fMRI data to somehow get started again, and also to basically set up what the remainder of the term will be about, because certain parts, especially with the introduction of random fields and family wise error rates in multiple testing and so on, they will get a little bit more involved, and it's good to, before going into the mathematical details of things, to review the intuition and where we are at overall. So the first thing, and that will be basically, I guess the first hour will be a review of what we've seen so far, because we've done quite a lot, and in the end, when we talked about REML again, I can think that things get a little bit lost in the details. So I first want to give an overview again where we are. So it's GLM for fMRI, obviously. That's what we've been doing since October. And what we are so far basically mainly concerned with, although of course things like maximum likelihood estimation and GLMs, they are general approaches, but what we've really been thinking of most of the time is the fMRI data, so the MR signal from a single participant in a single run. And for a single voxel. So this is what the data that we've been talking about all the time, and for which we set up a GLM model. So a series of, 400 data points that go up and down and represent data from a single voxel, so a single 3D location in the brain, from a single run when the participant did an experiment, and a single participant. So that's the data that we've been mainly interested in all the time. And for this data, we formulated a model. So the first big thing that we discussed, of course, in our trials of model formulation, model estimation, model evaluation, was model formulation. And the model that we formulated was, of course, the GLM. So we first looked at the GLM formulation in its typical form, where you have a data vector y, which is given by a design matrix times some parameters plus some error components, and these error components, or this error vector, is distributed according to a multivariate Gaussian and has a spherical covariance matrix, by which I mean this diagonal covariance matrix that is given by the multiple of a variance parameter with the identity matrix. Then we, of course, also discussed that this can be equivalently be expressed as a probability density function over the data. That is, of course, again, a multivariate normal distribution or Gaussian distribution with expectation parameter given by the design matrix times the beta parameter, and with covariance matrix parameter given by the covariance matrix of the error, which just follows from the linear Gaussian transformation theory. So that was basically how we started the sessions in October, and then we quickly moved on to GLM for fMRI, where this GLM now takes the form of a multiple linear regression, and the important thing is that the columns of the design matrix, so which I now write here as x1, x2, and so these are supposed to be vectors, where these columns of the design matrix represent the hemodynamic response function convolved condition onset functions. Yeah. So we spent some time to discuss how onset functions are convolved with the HRF and how this is a sensible approach under the assumption that the stimulus neural system bold response MR signal system is a linear time invariant model, and how these regressors are then formed, and that the associated beta parameters can be interpreted as the condition effects. We looked at these examples from different voxels that respond differently, and how their responses are then encoded in the, if you want, true but unknown beta parameters, and then of course also the estimated parameters. So when we talked about this, this is where we had this relatively long session on convolution, where the regressors for a specific time point I were formed by this convolution sum over the entries of the hemodynamic response function at time point 0 multiplied with the onset functions. In the actual text, the regressors are called YE because they're thought of as data there, or as the transformed sequence, and the X is the input sequence. Don't get confused there. So these things that come out of the convolution in FMI, they are the entries. They are the columns of the design matrix. And we've also, for completeness here, we also looked at the hemodynamic response function. So that was given by this difference of two gamma probability densities. If you remember in the script, so this then looked roughly like this. So it takes discrete inputs and then maps these discrete inputs to the difference of two gamma densities, where these densities have nothing to do with I'm just writing out the formula here, where these densities have nothing to do with probability theory. They just are used to create this analytical model of the hemodynamic response function. So everything that this thing here is doing that I'm currently writing up is to give you a function that looks like a hemodynamic response function that looks essentially like this. Yeah. So that's this double gamma, as it's often colloquially referred to, double gamma HF. And again, all of this to create the regressors of the design matrix. And this G function, G is the gamma density function. So that was our model formulation. Maybe to, unfortunately I forgot my mouse. So I can this to remind you of what this means in practice. Remind you what this means in practice is essentially to formulate, to put in the things into, especially the onset functions, into the respective mask in the, for example, the SPM software. It's the same thing if you use FSL for data analysis. And then what you end up with is, after clicking something like run, you create the design matrix, which you then can inspect, and this is what I want to show you. So initialize here. itself in this SPM structure, and you get this design matrix, which you can have a look at, and that's essentially it. So this is the formulation where we needed to, where we basically went via the specify first level, so meaning participant analysis, and had to fill in things like the timing parameters, and which basis functions, for example here the canonical HF, so which the convolution function, and the which onsets, which data we used. That's not really for the model, but which onsets we used. So this was all of this, and what came out was essentially the design matrix. What also comes out, and we will get to that in a second, is the covariance matrix, but we will see that in a second again. So that was basically the model formulation step, and once we had this in place, we then went to the next step in the model formulation, model estimation, model evaluation procedure, which is a fairly typical thing for probabilistic models, namely to do maximum likelihood estimation. And for maximum likelihood estimation, we first formulated the log likelihood function, which in general is a function from the parameter space to the real numbers, takes a parameter as input, maps it onto the value of the log likelihood function, which is defined as the log of the likelihood, and the likelihood just being defined as the probability of the data under the model with the specific parameters. Yeah, and because we had formulated this previously, so that was our normal distribution over the data, we basically already had our log likelihood function, and then we used the idea of maximum likelihood to choose that parameter estimate, which maximizes the log likelihood function over parameter space. And when we did this, what we ended up with were the for our model here, when we applied this to our general linear model, what we ended up with were the beta maximum likelihood estimator, which is a transformation of the data by essentially the design matrix multiplied by itself, inverted, and then transposed, applied to the data. And we also ended up with the variance, the maximum likelihood estimator for the variance parameter, which is given, on which we derived there, assuming that we know that, or that we have the beta parameter estimate, which is given by the residual errors. So the prediction error between the real data and the predicted data based on the maximum likelihood estimator, squared and summed up, divided by n. And then I already mentioned when we did this that this is not an unbiased estimator, and that an unbiased estimator is given if we don't divide only by n, but by n minus p, which is then also usually called the sample variance estimator. And we later then also discussed that this is actually the REML estimate, although I did not really show, and will also not show in this year, that you get to this formula with the n minus p when you apply the REML framework, because to do that, what you need to do is actually to do expectation maximization, and we don't discuss the expectation maximization algorithm in this year. So if you really want to know where the minus p is coming from, then have a look at the book at one point, or yeah, or try to Google it. It's actually not that easy to find where this is coming from. Anyway, so this is what we did for model estimation on a first pass, where we dealt the whole time with spherical error covariance matrices. And based on this, we then went into model evaluation the first time to basically introduce t-statistics, and t-statistics based on the distributions of the beta parameter estimator distribution, which we established with the linear Gaussian transformation theorem to be also normally distributed, unbiased, so the expectation parameter is the true but unknown value, and with this covariance matrix. And similarly, if a little bit less formal, we introduced the distribution of the scaled REML or sample variance parameter estimate, which was given by a chi-square distribution, mainly because here these normal distributed things are squared, so they cannot be again normally distributed, but will always be positive, so they don't have a normal distribution, but they have a chi-square distribution with n minus p degrees of freedom as parameters. So based on these estimate distributions, we then introduced t-statistic. So we then came to the t-statistic, which for a given contrast weight vector c was given by this ratio of the difference between the estimated parameters and some hypothesized parameter values, for example 0, if you do a t-test against 0. So this effect size or effect measure divided by the measure of the variance. So that the basic intuition of a t-value is that it's how strong the effect is compared to an estimate of the variance of the effect. The nice thing about the t-statistic, in addition, because it's basically formulated in terms of this thing, so the beta parameter estimate and the variance parameter estimate, and the distributions of these are known, and then you combine these distributions, this thing then being distributed according to a t-distribution with n minus p degrees of freedom. And we've also looked in some details into this. And yeah, basically then ended up there when we did our first pass-through model evaluation with the idea that we now have this univariate outcome of some parameter contrast. So for example, if you have two conditions, beta 1 and beta 2 in your design, and you want to know whether there's a significant difference between them, that you use a contrast vector of the form -1, 1, and then you basically can test whether the difference, if we have it this way around, then we have beta 2 minus beta 1 equal or not equal to 0. Then based on observed t-statistic, with so far the main intuition that if the t-statistic is quite large under this null model, that the null hypothesis that the contrast, so this product of the contrast weight vector with the beta parameter is 0, is unlikely. And in the remainder of this term, we want to go a lot more into detail about this idea of statistical testing. So for now, we've only established that there is something like a t-statistic, that it has a given distribution, but we have not really formalized what a test is. We also haven't talked about this thing that we are not only testing this at a single voxel, because so far we've only talked about a single voxel, but we test these hypotheses at all voxel locations in the brain, which then induces a multiple testing scenario. And a big part of fMRI data analysis, statistical analysis, is then how to account for this multiple testing problem. And the standard approach that is implemented in all the softwares is random field theory, based p-value evaluation or random field theory. And this is going to be a big topic then for the remainder. So this was our first pass into model evaluation, but then we went back to model estimation and also model formulation in a way, because we introduced this idea that not everything that is happening in the data is accounted for in the design matrix, and we introduced this idea of error correlations. And with error correlations, we basically then went from the idea of a spherical covariance matrix, so from the sigma square IN as the covariance matrix of the errors. We can write like this, maybe the other way around. That's more intuitive. So we went from assuming that there's no correlation between the errors to the idea that there might be correlation between the errors, and the question of what to do then. And this, of course, meant that we changed the model, the formulated model. We also seen that if we would now proceed with all the equations and the t-distribution as is, that we would be misled to get false positives, because our t-values will be in general too high compared to the analytical distribution. So we basically needed to go back to the whiteboard and or blackboard and think again. And there we discussed two cases. The first case that we know the error correlation structure, so that we have precise knowledge of it. So we don't have a free parameter in this case. Maybe we have a scaling parameter, but in general we have a full knowledge of the error correlation structure. And in this context, we introduced generalized least squares estimation and data widening, where the basic idea was that, well, and the main idea in terms of data widening was, if we know, if we have a GLM of this form, and we know V, and we also know that it's not the spherical error covariance matrix, which would allow us to just use standard inference in terms of the t-distribution. That what we can do is to widen the data and do inference on this widened data, where the main idea was to first decompose the V matrix into its square root, if you want, to define a widening matrix as the inverse of K, and then apply this to our non-wide GLM. So this is what we discussed when we discussed generalized least squares estimation, where we start like this. So we have a non-spherical GLM, or a GLM with non-spherical errors. Then we multiply this whole thing with our widening matrix. And then we get this new GLM, which is the multiplied GLM just written up again so that it looks like a normal GLM. And the main thing here being that due to this definition of the whitening matrix and the fact how covariance matrices transform under multiplication, we get to a spherical GLM again. So we get again here, and this means we can use standard t-test again, or standard t-inference. Now, this was of course under the assumption that we know this variance matrix, and of course that's not really realistic, because that's also part of the model and not directly observed. What we observe is the data and not its covariance matrix. So this is why we then, and this was the last thing that we did before Christmas, if this covariance matrix of the area is not known, we went into this business of covariance component estimation, which was then combined with REML. So this was then the thing that we did before Christmas. And here the main thing is that the error covariance matrix is not known. So what we did then is to say, okay, it's not known, so let's model it, and we model it as a sum of covariance components, where if you read the literature, it's not quite clear what these covariance components are. So what I called things are here these covariance component parameters, which we actually estimate using REML, and the covariance component basis matrices. And if you just hear the term covariance components, it's not necessarily completely clear whether these matrices are meant or whether these parameters are meant. And so basically we imposed some structure on the error covariances, and then used REML in its Fisher scoring implementation to estimate these. And this I'm not writing out again. This was basically what we did in the last hours before Christmas. Estimate with REML Fisher scoring, for which we needed to basically, to understand what Fisher scoring is, we needed to understand what Newton-Raphson estimation is, and what the Fisher information matrices are. And once we have estimated these values, so once we have our estimates for these lambda k, then and this is actually how it's done in the SPM software, then these are pooled over voxels, and we get an estimate of the error covariance matrix, which is then just given by these estimates derived from this REML algorithm multiplied by Qi, and then they are treated as known, and we can do data whitening. So then we basically go back here, and then for every voxel we treat the error covariance as if it was known, because we've estimated from really many voxels, and can use again the t-distribution for inference. So this is essentially what we've done from October to Christmas. Again, from the practical perspective, what this amounts to is the formulation of the GLM, also in terms of the covariances, this thing with the covariance component or basis matrices, where the first one is the identity matrix and the second one is this exponential of the difference between time points, which I introduced but so far haven't justified, and will only be able to justify once we talked about random processes and random fields. Where this is showing up is in this serial correlation. This is very weird, but this is where this is showing up. If you decide for AR1, this is where you set up the covariance matrix structure and then lead this whole thing into in a GLM with non-spherical covariance matrix, and then induce thermal estimation. This whole estimation business, then once everything is formulated, happens fairly easily by clicking estimate and override. And then what SPM tells you is that it's estimating the non-sphericity, and this non-sphericity, because it's CAL, applies to two things. It's the temporal non-sphericity, which is the non-sphericity of the errors, and later on it also estimates so here's where it's estimating the temporal non-sphericity using REML. And then at a later time point, actually at this time point here, it's also estimating the spatial non-sphericity, which is part of the random field business, which we haven't discussed yet. So there's one function that does both sphericity estimations, and then at one point, fairly quickly actually, it's estimated over the whole thing. So spatial non-sphericities, which we haven't discussed yet, and then the model is estimated. And so this is everything that we've done so far, which is quite a lot, but so far obviously you don't see any blobs in the brain, so nothing, the results are not really there. And the results then relate to what we want to do in the remainder. So let me first tell you what we are now going to do until mid-February. And as the last part of this classical, of this GLM-based fMRI analysis, before in the summer term we'll go to the machine learning analysis of fMRI data or neuroimaging data. So the remaining things to discuss this term are now that we have evaluated parameter estimates of the GLM for each voxel, and we have ensured that the t statistics that we can form on these parameter estimates, so on the beta and the variance parameter estimates, these t statistics are actually t distributed because we have accounted for temporal autocorrelations using whitening. Then we now want to do a formal statistical testing, so to decide essentially whether for each voxel there is actually activation or not. So the first thing we want to discuss is statistical testing. So what does it actually mean to do statistical testing? And then, of course, with fMRI data, we have not only a single voxel, as we've treated everything so far, but the estimation already happened for all the voxels, but one after the other. So it's essentially talking about the estimation in one voxel. But now when we evaluate the t-test and then look at a statistical parametric map where we have all these statistics together, then we need to account for this multiple testing problem, and we have to discuss what that means and what it means to control the family-wise error rate in general. So that will be the first thing, and this is also in the next hour with which I want to start. And then the next thing, after we discuss what statistical testing actually means, we will discuss the approach that is used in neuroimaging to deal with the multiple testing problem, which is based on random field theory. So for this we have to introduce the idea of random fields and how they are used for family-wise error rate correction or for multiple testing control in neuroimaging. So this will be the main thing to discuss until February. One thing that I hope to put in at one point is, once we know what a random field is, and when we know what a random field is, we also know what a random process is, because it's a special random field, that at one point I can give you the account of why this autocorrelation function in the first level has the form that it has, because this can only be motivated based on random processes. So this is referring to this second basis function in, I think it was that, no, it was different, it doesn't really matter, so I think it was Q2 was ZT or something, which had this exponential in the difference between I minus j or something like this, where this is coming from. So this has to do with stochastic processes or random processes, and this we can sneak in. But so this, now I'll talk more about this. The most important and the biggest chunk that we're going to discuss is definitely this. This is what we do first, and at one point I will sneak that in, because we can then, once we know what a random field is, understand what's going on there. So in terms of the practical aspects of fMRI analysis, this is of course all model evaluation or parameter inference based on the model, and what this really relates to is what you do when you do the following. You've now estimated a GLM, and then you want to look at the results, and of course you need to define a contrast. So here we have three beta parameters: beta 1, beta 2, beta 3 for each of the columns of the design matrix, and I'm now interested in whether the beta parameter for this first column, which were, if you remember, these were checkerboards that were shown at specific times to a participant, and these were also checkerboards but of lower contrast, whether the sum of these two betas is larger than 0. So I define a new contrast where I want beta 1 plus beta 2. So I take the contrast weight vector 1, 1. And from this get the contrast beta 1 plus beta 2 larger or unequal to 0. And now I test this for all the voxels in the brain by clicking OK. And this is just specifying the contrast weight, and then basically saying that I want to evaluate this contrast in terms of t values all over the brain. And then I have to, in fMRI data analysis, do a little bit more, because this then relates to the random field theory business. Masking is not that important. What is important is that I have to define, and this is what I'm doing with these two clicks here, I have to define a cluster defining threshold, which is just, so if you think there's this SPM with all the t values now, because I specified a contrast, so each voxel has a t value now, as you also remember from this first lecture on mass univariate fMRI. Now I'm thresholding this map, So this brain map at a given value. So the t-values, they range between -10, let's say, and +10, and I'm obviously interested in the ones that are very positive. So I'm thresholding it at around 4. This is done via p-values, but we can actually define a t-value, I think. So let's threshold it at 4. If I want to do a certain kind of test which relates to set levels, I can also give a voxel threshold. Again, this is part of the random field theory business that we need to discuss. And then once I've done that, I end up with this map and this table. And it's essentially this table that in terms of random field theory we need to discuss. Because this table has 3 levels of inference: peak level, cluster level, and set level. And the question is, what does that mean? It has the t-value at a given voxel here. That's something we can understand already, because this now has a t-value. It's the beta 1 plus beta 2 divided by the variance. Has a high t-value here. But then it also has p-values associated with it, which are uncorrected and family-wise error corrected, and we don't know what that means yet, what that means, or what these values mean. Then it has something called cluster level, and what you mostly find in fMRI publications is that people report family-wise error corrected inference at the cluster level. So what they do is they look into this table and select the clusters and report them that have a p-value smaller than 0.005 in this column here, because that usually gives you more things to report. What this means we also don't know, because it relates to the random field theory framework, and then the set level, which we also don't know what that means. Here you can see that the threshold was chosen as 4. Here's some expected voxels per clusters, numbers of clusters, and so on, full width, half maximum. All these things are things that relate to the random field theory business, which we now want to basically discuss. And what you also can do if you like to do things like that, you can of course put things on, put this map on, overlay it on some anatomical image, and then you see some blobs on the brain. But these are of course just these clustered and rendered onto an anatomical image, and the result of a fMRI study is not an image like this, but it's the table. And what this table means, which is the end result of classical fMRI analysis, this is basically the topic for the next 6 weeks. Yeah? Questions after this monologue?
I have several questions I will share about, but there is probably time for all of them now. Should I start after we are taking a break?
So what are your questions?
For example, there are at least 7 or 8 questions. Maybe the general ones regarding the script. There are some things in the script that you didn't discuss in the lecture. These things have also corresponding study questions.
Okay, so that's a question about the exam. So what I've been, what I did already is have a look at the script again, because I took out certain parts that I didn't discuss. So for example, there was something on design matrices and orthogonal, non-orthogonal stuff. I took out these things, so this is what I'm taking care of, so you don't have to worry about this.
So what is relevant to the exam is only what you discussed?
Yes.
Okay. And in the script, there are that chapter on restricted maximum likelihood estimation, there are no study questions for this chapter. Will you add something later for the example?
There are no questions there, you say? Yes. So far, I think because this was kind of a novel section, there will be 5 questions for that. Yeah. Don't worry about the exam. Okay. We'll be fine.
Should I start with the questions
Yeah.
For example, from the very first chapter, there was something about sampling 400 data points, and with data points we probably mean measured bulk measures from the fMRI 400 for one voxel. So this would mean a 400 dimensional sample from 400 dimensional Gaussian. It's also mentioned that this is equivalent to 400 random data points from a one-dimensional Gaussian distribution. How would we conceptualize this if you wanted to sample 100 data points for several voxels?
No, we don't. So that's the point.
Okay.
So I mean, one can generalize multivariate Gaussians to how they call it. They have a different name. It's about sampling matrices. So basically sampling Gaussian matrices, but we don't. So this is the whole point of this mass univariate approach that we did so far. That we only sample multivariate Gaussians and voxel by voxel. What will happen now when we talk about random field theory is that we actually stop thinking about the 400 data points from a single voxel, but now we've collapsed things, as you can also see here. We collapse things to t-values, and what we will now talk about is a field of t-values. So we talk about t-values being sampled over space. So this is when we now go into the spatial domain. We view what we've done so far as a computational simplification and create basically a new model, or a model that we had in mind all the time, but we basically evaluated computationally efficient. We have this new model of a field, so a spatially extended random process of T statistics, or Z statistics, as we will see.
Yeah, okay. And regarding the GLM and the method in general, I've wondered why one doesn't simply average voxels for a hypothesized region of interest, like one does, for example, in psychometrics, where one averages several questions that are thought to represent one construct.
Yeah, one can do a region of interest analysis. The thing is, in general, so in terms of brain mapping, and the question is what you then want to do. I mean, you have if you have a region of interest, you would have to have a good story why you are now interested in it. For visual cortex, you usually have that, so that makes sense. But the more general question that is answered by brain mapping is the brain does a task, which areas in the brain are involved in that task, and then because you measure the whole brain, then why not evaluate the whole brain? And this is why region of interest analysis are done mainly in the vision science, because people there only look at the visual cortex. The other thing is, if you acquire that much data and then you throw away most of the data, and the question is why you first acquired it. So,
yeah. For example, in one sample when we compared two regions and their activation, when we formalized the GLM model, there we hypothesized that one voxel belonged to a certain region and the other one the other region, and we hypothesized different activations. Why wouldn't we? And here we had some hypotheses about the regions. Why not simply average the several voxels belonging to each region and then compare them directly?
No, well, so the thing with averaging about regions is, first of all, there is some sort of averaging over regions in the smoothing step of the pre-processing. So the regions that you can detect, of course, based on this match filter theorem, they somehow have to have the size of the things that you are later looking at under the smoothing constraints that you also need for random field theory. The other thing is, per se, you don't know what are functionally relevant distinct regions. So, I mean, of course, you can have some anatomical constraints, but there's, of course, no guarantee that this is also functionally interpretable. And that's the main thing. And the other thing is, of course, once you have the result, and this was also the result with these two voxels there, once you have something like a map like this, of course, you can do regional inferences. And this is the main point, of course, that you, for example, say, okay, here there was in this very simple example, there was left visual hemifield checkerboard stimulation, and now primarily right visual cortex is active. So then, of course, you say, okay, the right visual cortex is more active than the left visual cortex. I mean, you do these kind of regional inferences, but if you always want to average, you would have to have a good parcellation scheme for the brain in the first place. And if you try to figure out what are the functionally relevant regions, you don't have that before, so you need to go via the entire voxel set.
In undergraduate statistics, we always had normal distribution as an assumption for right-hand-test for normal t-test. In our conceptualization, this is equivalent to spherical covariance matrices, right?
No, normal distribution is just Gaussian distribution, and if you in undergraduate statistics had independent and identically distributed data from normal distributions, that would be equivalent to multivariate normally distributed data with a spherical covariance matrix.
The assumption was that the dependent variable should be Gaussian, normally distributed. Is this equivalent to?
No, this is what they always say in undergrad statistics, but this is a misunderstanding. So in undergrad statistics, what they mean is that the errors are normally distributed. But they often say that based on this, it's somewhat equivalent, but the independence is in the errors and not in the data points, and this is the important difference. So if you look at this here, here the errors are Gaussian distributed, and the data are also Gaussian distributed or normally distributed. The errors are identically and independently distributed. They are identically distributed because they're all centered on 0, and they are independent because they come from this covariance matrix. The data, they are not identically distributed because in each entry of the expectation vector, there you have this product of the corresponding row of the design matrix with the beta parameters, and because the design matrix changes, also the entry in the expectation vector changes. So, which also means that if you analyze just the data per se, because there is dependency, for example, between adjacent data points based on this mean shift, that the data points are not independent. So this is a misconception in undergraduate psychology statistics, that people always say that the data are normally distributed, or they are normally distributed, but the important thing is this, the errors are normally and independently distributed. This is the important thing.
We wanted to take the MRI signal not as a dependent variable, but as an independent variable. So here we would have an independent variable that isn't really deterministic for conditions. Would we have to define error terms for the independent variable?
Now what this relates to is, so if you want to do that, so if you want to correlate one voxel's time course with another voxel time course, you are in the business of correlation and not regression, and the idea in correlation is that both your dependent and your independent variable are random variables, and hence you look at bivariate distributions and you look at correlations. We didn't discuss that at all. One thing that is often done is that the subtlety is somewhat neglected, and for example, if you do things like psychophysiological interaction analysis, so PPI analysis, you use voxel time series also in the GLM. And of course, simple linear regression and correlation are really, really closely related, but the interpretation of the independent variable is different. I didn't discuss the difference between simple linear regression and correlation here, so that can be done. One sees a lot of similarities in terms of the formulas that come out, which also means that correlation is a measure of linear dependence. But as you say, in regression and in the GLM, the independent variable is not a random variable, but it's deterministic. And here it's of course always deterministic because you choose how it is because it's your experimental design.
In the maximum likelihood estimation, when we estimate the beta parameter, is this beta parameter equivalent to the beta weight in a regression analysis?
Yeah, sure.
Okay. And how do we come to the intercept? Because we didn't.
The intercept. So if you think about simple linear regression. So in the very beginning we discussed simple linear regression where in the design matrix we had a column of ones and a column of the values of the independent variable. Of course there we had two beta parameters, one beta parameter related to the independent variable and one beta parameter related to this column of ones. And this column of ones of course adds 1 times this beta parameter to every data point and then reflects the intercept. So the intercept, you also see that here in the design matrix, here this is a column of only one, so this is modeling the offset.
Okay. Yeah, and also we had in regression analysis and regression statistics, we had standardized beta weights and normal beta weights. Is this something?
The only.
The standardized beta weights were also equivalent to the correlation between the dependent and independent variables we usually have.
Yeah, this relates to this is not really important here, but this is about this how to relate simple linear regression to correlation. So I think so we are not discussing that here, but this makes some sense because correlation and simple linear regression are essentially the same thing, but you need to adjust the parameters, which then will relate to this, what you just said.
But yeah, what we talked about, what we estimated with the maximum likelihood estimation is non-standardized.
It's just the beta parameters of a GLM.
Regarding the t-statistics, you define it as a measure of the effect divided by the variance, but the t-statistics is usually divided by the standard error, right? No? It's the standard deviation?
It's the t-statistic is I know what you mean. So sometimes you see this formula for the t-statistic where the standard error of mean plays a role. But this is already, so this is, now there I would suggest that you read closely the script because this relationship between this formula and this classical formula of a t, like you know it from undergrad statistics, of a one simple t-test, t-statistic, this is explicitly in the script. And essentially where this division by n comes in, which then, so when you relate the sample variance, so here you have this sample variance, then you have the square root of it, so you have the simple standard deviation, and then you divide, for the standard error of mean, you divide by the number of data points, the square root of the number of data points. This is in this term, but this is written up all in the script, so have a close read there.
I read it, and here we define, for example, t-statistics is a measure of the effect size associated with the independent experimental variable measured relative to the data variability. But you also said in the lecture that relative to the data variability and the sample size, the sample size has an effect on, in contrast to the Cohen's d, for example.
Yeah.
But you described it as annoying. But do you see it only as annoying, and do you see it as a mathematician? Don't you think that its effect, for example, when comparing t values from different studies that have different sample sizes, don't you find that? Don't you think that it would be better to compare Cohen's d's between studies?
I think what I find, I don't know what I find annoying, but I find a lot of things annoying. But what I always, so in psychology statistics, there's a big fuss about Cohen's d, and Cohen's d is just a a transformation of t-statistics. So t-statistics and Cohen's d are equivalent. If you know the sample size, then you can transform one into the other. So so there's no magic, and so t-statistics are fine. T-statistics are measures of effect versus variance as Cohen's d. The only difference is that t is dependent on the number of data points, but of course the number of data points is related to the variability. So more data points, less variability. Yeah. So let's not discuss that further, please, because there's nothing in there. There's nothing to discuss.
But I mean, when there are meta-analysis for FMR, do they usually use these statistics when computing the
I don't know what
results?
They will have their methods to do proper meta-analysis. We would have to look into them. I'm not an expert on meta-analysis.
Yeah. Okay. I have a specific question to the graphic and the script, which you also.
So how many more questions do you have? Because I think we have to stop now.
Yeah.
So I would suggest that you come to the lecture in the morning and ask your questions here. No, not these questions, but questions that you have. So you come here and that you read things, and that then we can discuss that here, because it's useful. So I like the questions because it helps to clarify things, but it's would make more sense if you would come weekly and ask a couple of questions. Yeah? Good. So there's one more question.
Yeah, regarding this does the spatial resolution of our MRI data affect the probability to get a significant effect in terms of t-tests, or how does it?
Yeah. So yes, this is then of course the topic of random field theory. So the t-statistics that we evaluate in a given voxel, they just depend on the data in a given voxel, and also remain constant. But if you now want to evaluate the statistical significance, you first need to know what statistical significance means, and how essentially this is evaluated in fMRI. And this is in the random field theory business. It then depends essentially on the physical search space, so how many voxels there are, and on the smoothness of the random field. But this is all stuff that we're going to discuss now. Yeah. Good. Then let's have a break now, and then do half an hour of statistical testing from 9:15 to 9:45.